Good morning, I am Devasena. In this lecture, we are going to discuss about analysis of series circuits. This topic is present in the subject circuit analysis. Now we are going to discuss about the analysis. A series circuit is one in which several elements such as resistors, inductors, capacitors, etc. are connected one after the other. Such connection is also called end-to-end connection or cascade connection. There is only one path for the flow of current in series circuit. Let us discuss about resistors in series circuit. Consider the resistors as shown in figure. In this figure, the resistors R1, R2 and it goes on up to Rn are connected in a cascade manner. That is, one end of the resistor R1 is connected at one point. The other end of the resistor R1 is connected to R2's one end, and the connection goes on as shown in figure. And for all these resistors, the current I is same. That is, equal amount of current is flowing to each resistors. But the voltage drop across these resistors varies, depends on the resistance values. This is indicated in this diagram. The resistance R1, R2 and R3 are said to be in series. The combination is connected across the source voltage V volts. Naturally, the current flowing through all of them is same, indicated as I amps. Example, the chain of small lights used for decoration purposes is good example of series combination. Let us study the voltage distribution across each resistance. Let V1, V2 and V3 be the voltages across the terminals R1, R2 and R3 respectively. Now, according to Ohm's law, V1 is equal to IR1, V2 is equal to IR2, V3 is equal to IR3. Current flowing through all of them is same, that is I. Therefore, V is equal to IR1 plus IR2 plus IR3. That is nothing but I into R1 plus R2 plus R3. Applying Ohm's law to overall circuit, V is equal to I into R equivalent, where R equivalent is the equivalent resistance of the circuit. By comparisons of the two equations, R equivalent is equal to R1 plus R2 plus R3. That is, total resistance is the sum of resistance connected in series. For n resistance in series, capital R is equal to R1 plus R2 plus R3 and it goes on plus Rn. Let us discuss about the characteristics of series circuit. The same current flows through each resistance. The supply voltage capital V is the sum of the individual voltage drops across the resistance. That is, capital V is equal to V1 plus V2 plus V3 and it goes on up to Vn, where V1 is the voltage drop across the resistance R1, V2 is the voltage drop across the resistance R2, V3 is the voltage drop across the resistance R3 and Vn is the voltage drop across the resistance Rn. The equivalent resistance is equal to the sum of the individual resistance. The equivalent resistance is the largest of all the individual resistance. Let us discuss about inductors in series. Consider the figure shown below. In this figure, we have inductors L1, L2, L3. One end of the inductor L1 is connected to the terminal A. The other end of the inductance L1 is connected to the inductor L2. The L2's other end is connected to one end of the L3. L3's other end is connected to the terminal B. The three inductors L1, L2 and L3 are connected in series. The currents flowing through L1, L2 and L3 are I1, I2 and I3, while the voltage across L1, L2 and L3 are V1, V2 and V3. We have V1 is equal to L1 dI1 by dt, V2 is equal to L2 dI2 by dt, V3 is equal to L3 dI3 by dt, while VL is equal to L equivalent di by dt. For series combination, I is equal to I1 is equal to I2 is equal to I3 and VL is equal to V1 plus V2 plus V3. Therefore, L equivalent di by dt is equal to L1 di1 by dt plus L2 di2 by dt plus L3 di3 by dt, that is equal to L equivalent di by dt. That is, L equivalent value is equal to the sum of L1 plus L2 plus L3. That means equivalent inductance of the series combinations of three inductance is the sum of inductance connected in series. For n inductance in series, L equivalent is equal to L1 plus L2 plus L3 plus it goes on up to plus Ln. Consider the capacitors in series figure shown below. Three capacitors C1, C2 and C3 are connected in series. The currents flowing through C1, C2 and C3 are I1, I2 and I3, while the voltage across C1, C2 and C3 are VC1, VC2 and VC3 respectively. We have V1 is equal to 1 by C1 integral of minus infinity to t I1 dt. V2 is equal to 1 by C2 integral of minus infinity to t I2 dt. V3 is equal to 1 by C3 integral of minus infinity to t I3 dt. While the total voltage V is equal to 1 by C equivalent integral of minus infinity to t I dt. For series connection, the same current is flowing through the circuit. That is, I is equal to I1 is equal to I2 is equal to I3. And the voltage across the capacitance V suffix C is equal to the individual voltages across each capacitors. That is V1 plus V2 plus V3. 1 by C equivalent integral of minus infinity to t I dt is equal to 1 by C1 integral of minus infinity to t I1 dt plus 1 by C2 integral of minus infinity to t I2 dt plus 1 by C3 integral of minus infinity to t I3 dt. But I is equal to I1 is equal to I2, that is equal to I3. That is 1 by C equivalent integral of minus infinity to t I dt is equal to the sum of 1 by C1 plus 1 by C2 plus 1 by C3 into integral of minus infinity to t I dt. That is C equivalent is equal to C1 C2 C3 divided by C1 plus C2 plus C3. That means reciprocal of equivalent capacitor of the series combination is the sum of the reciprocal of the individual capacitance. For n capacitors in series, 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus it goes on up to plus 1 by Cn. As a summary, the current flowing through the series circuit is same, but the voltage drop across the element in series circuits differs depending on their values. For n resistance in series, the equivalent resistance R equivalent is equal to R1 plus R2 plus R3 plus goes on up to plus Rn. For n inductance in series, L equivalent is equal to L1 plus L2 plus L3 plus it goes on up to Ln. For n capacitance in series, 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus it goes on up to 1 by Cn.